All right, last but not least, this is a equals b squared over r, take 3, which is going to use calculus, be forewarned. It's not terribly hairy calculus, but it is calculus. So, without further ado, we are dealing with uniform circular motion here. I will dispense with the pleasantries. And let's say we are starting from the center here, and we want to see the object moving through a small, well, I'll say the object, okay, so here's our position vector, right? Pointing at our object. I'm going to say that's our object. I'm going to draw it in blue this time. I've been drawing in red before, but I think you get the idea. Okay, so, and we know the magnitude of r is, which is just, scalar r, is constant. All right, so what we want to do is we want to set up some coordinate vectors, or a coordinate frame that is centered on the circle and runs horizontally and vertically. So we're going to call this here x, we're going to call this here y. And so we want to express this vector r in ij notation. We say r equals, so it's got some distance from the beginning, right? And then we just want a, at some, or at some position theta, let's call it. So let's say, here's another r, and it's at some angle, theta from the horizontal. It's going counterclockwise, so it's some angle theta. All right. So r equals r. The horizontal component is going to be r times cosine of theta, right? It starts at 1 when theta is 0, and then theta equals pi over 2. It's gone down to 0, and then it becomes negative 1, and then 0, positive 1. So it is r cosine theta I hat, and then the j component, or the vertical component, will be r sine theta times j hat. That's easy enough, right? Does that make sense to everyone? Okay, so I can't hear you, so it doesn't matter if it doesn't make sense. I'm going on. But anyway, this is how it works. Now, first thing we want to do is, well, what we really want to do is we want to find the velocity first, and the velocity is the derivative of position with respect to time, right? Well, we don't have an expression for time. We do know though that theta is changing with time, and we know it's changing at a constant rate. It's sweeping out at a constant rate here, right? So theta equals omega times, what I'm going to call omega our angular velocity. So theta equals omega times t. So theta has imagine, well, sorry, not theta. Omega, imagine, well, not imagine, it does. The units of omega are radians per second. So if we're doing theta in radians, and then t is in seconds, right? So the units of omega in SI units is radians per second. It's angle divided by time is what it's its dimensionality. Okay, so to find this, to find dr dt, which we can't do directly because we don't have r as a function of time. What we do instead is we do v equals dr d theta times d theta dt. Simple enough, right? So, what's dr d theta? Well, derivative of cosine theta is negative sine theta, right? So it's negative r sine theta, and that part was times I hat. The I hat and j hat are constants. They don't differentiate with respect to anything. And then the derivative of sine, r sine theta times j hat is cosine. So plus r sine, oh, sorry, whoops. So let me just write over that really dark. R cosine theta j hat, and that is our velocity. Well, sorry, that's not true. That's our dr d theta, and then all that gets multiplied by d theta dt. What's d theta dt? Just omega, right? So let's write this again one more time. Velocity equals negative, and I'm just going to distribute this. So negative omega times r, and I'm just going to collect everything here. So this is an r. So actually, you know what? Let's just get rid of this negative here. Let me see if I can erase. There we go. Okay, omega r. Excellent. Omega r times negative sine theta times I hat plus cosine theta times j hat. All right, that's convenient. So that's our velocity vector. What is what is acceleration, right? Acceleration is just, and I'll switch to my acceleration color. Acceleration is derivative of velocity with respect to time. Okay, but like before, we don't really know that directly. So, hi. All right, pardon the interruption. We don't really know that directly. So, well, we don't have this in terms of t. So what we have to do again is just differentiate with respect to theta, and then multiply it by d theta dt. Okay, so dv d theta is then omega r, and then the derivative of negative sine with respect to I hat is negative cosine theta. I'm sorry, with respect to theta, negative cosine theta times I hat, and then derivative of cosine is negative sine, so minus sine theta j hat. Okay, and then the d theta dt is again just omega. So scrolling down a wee bit, let's get down to about there. Okay, so this gives us a equals omega r, it's actually omega squared r times negative cosine theta I hat minus sine theta j hat. Alright, there we go. Alright, so now recall from above, this up here, right? We can really write that as r vector equals r times cosine theta I hat plus sine theta j hat. And now you notice this in here, oh, I don't know what's a good color. Let's go to the sort of browny stuff. This in here is just the negative of this in here. That was a little bit spastic. There we go, it's a little better. So what you can say actually is then r hat equals r times this, and a equals omega times this. So what you can actually say, this is even more convenient, this is super convenient in fact, is that your a vector equals, let me see, well, yeah, all right, a vector equals negative omega squared times your r vector. Okay, so now the only question remaining is, what is this omega squared? Well, omega is, you recall, the rate at which you are sweeping around the circle, right? So omega is d theta dt. So recall it was theta equals omega t, and so you are swooping around the circle at a rate of omega, right? So well, omega, so theta goes through 2 pi in one period. We're going to approach it from this way. So 1 period of the rotation, actually let me do it in black. So 1 period of the rotation, capital T, times omega is 2 pi. This is just, I kind of swap the sides here, so you have to look at it that way. But theta, when theta gets up to 2 pi, omega has been multiplied by capital T. So omega equals 2 pi divided by t. But now remember from above that the period is the circumference of the circle divided by the speed at which you're going around, right? So t equals 2 pi r over v. We plug all this in. This is not the most elegant way to go at this, but omega 2 pi over this, which is 2 pi r over v, so we can put the v up here actually, cancel those, and then omega equals v over r. So bring all that back up here, and what we get here is our acceleration vector is negative omega squared, so negative v squared over r squared times the r vector. Now if we just want magnitude, so this is one equation we can save if we really want to. If we just want magnitudes, then we take the magnitude of both sides. Then we get A equals negative v squared over r times r. So we just take the magnitude of this side, magnitude of this side, easily enough. And then A equals negative, oh, I'm sorry, that's an r squared down there. So then A equals negative v squared over r. And so there's our third and final proof of v squared over r.